All right, hi everyone. Thank you so much for coming. My name is Alice. I am an engineer on the emerging products team here at Pinterest. To give you some context, I've been at the company for a little bit over 2 years now, and in that time, I've also worked on the search team and the explore team.
Hi everyone, I'm Sam and I work with Alice. I've been at Pinterest for almost 3.5 years, and I started out in growth engineering and currently working with Alice in emerging products.
So today we're going to talk about how we built reordering pins at scale. Here is a quick overview for those of you who might not be 100% familiar with our app. Pinterest is a space for you to discover and do ideas that you love. So for me right now, that means finding a lot of inspiration for my bedroom redecor and also pinning pictures of cute animals as usual. Our feed is made up of these underlying visual units called a pin. And you can save a pin to your board. A board is essentially just a collection of pins that has some additional features built on top, including collaboration and privacy settings. And previously, pins would always show up on your board in the order that they were saved, from most recent to least recent, and there was no great way around that. So why did we decide to build out pin reordering, and why choose this feature to work on out of all of them? Well, our users had a lot of strong opinions. We got a lot of angry tweets, such as this one from Felicia Day. The fact that you can't drag and rearrange pins on Pinterest is reason to never use the service again. So dumb. Hashtag my secret throw pillow board. Well, it turns out Felicia wasn't alone. A lot of users felt similarly, and every day we would get a bunch of user requests asking, begging us to build out pin reordering. In fact, for the past 6 years, pin reordering was consistently one of our highly requested features. So we really wanted to put our pinners first and listen to them.
So we went out and built a feature, and this is what one of the implementations looks like on iOS. So you can drag a pin from any position and drop it into the new position that you want it to. And then after you let go, the change is saved right away. So before we started, we came up with a couple requirements for this feature. So as you saw earlier, users can drag and drop a pin between any two other pins. You can also drag it to the front or at the very end. Also, the changes should persist immediately. So after you let go and pull to refresh, you should see the new your new board ordering. And the solution should also scale across very large boards. We have some pretty large boards at Pinterest. Some even have like millions of pins. And we should also support many reorders within a short timestamp, maybe say 1 second. So this is a schema for our board has a pins table. It's a MySQL table that stores the relationship between pins and boards. And we have three major columns. The first column is pin ID. This is the ID of each pin. And the second column is the ID of the board that the pin belongs to. And finally, there's a sequence column that determines the ordering of the pins in the board. And it's initialized to the timestamp in seconds of when the pin was created. So we actually considered several approaches before settling on one. So I'll just go through two of them. And the first approach we called batch increment. So we can visualize this approach with 5 pins, and the numbers here are the sequences of the pins from 6 to 10. And in this example, we want to drag the pin at 7 in between 10 and 9. So you can see that 7 is now out of order, so we need to update the sequence so that it respects its new ordering. So what we could do initially is set the sequence of 7 to its right neighbor 9. And then we can cascade this change down to its neighbors. So you saw earlier 9 was tied, so we could decrement the right neighbor to 8 and proceed to keep decrementing until we reach our original drag position. So this is, now it's in order. So this is what it looks like in SQL. So first, we grab the sequence of the right neighbor, or the destination that we're dragging to, and then we update the sequence of the pin we're dragging. And then we just proceed to decrement all the pins starting from the pin next to the right neighbor all the way to our original drag position. And this is a batch update that writes to multiple rows. So this solution works, but there are several problems that we saw with this. One is that it requires writing to multiple rows for every reorder. And if the drag distance is large, this could result in many row updates, resulting in large write load. So this is a case, especially if we made the API available to our partners to call directly. They could call the API with in such a way that the pin could move like thousands of spaces away. So we consider another approach, and this one we called gap bisection. So again, in this example, we're dragging the pin at 7 between 11 and 9. And instead of updating the sequence to a neighbor, we just take the midpoint between the neighboring pins. In this case, we take the midpoint of 11 and 9, which is 10. And so that works, but what about dragging to the front or back? So we could update the sequence to be one above the leftmost edge, but to save an extra read, you can recall earlier that we initialized the sequence to be the timestamp of when the pin was created. So we take the current timestamp that's guaranteed to be greater than all the existing sequences. So in this case, we update the sequence to be the current timestamp, which saves us an extra read. And we can do the same thing we're dragging at the end. So you can sort of foresee a problem like eventually we can only bisect. We can keep bisecting, but what if we reach a point where the gaps are too small to be divisible? So in this example, the neighbors are 11 and 10, and assuming integer resolution, there aren't any numbers available for us to bisect. So you can see if we choose 10, there's a tie, and then the ordering is no longer guaranteed. So our way around this was increasing the sequence resolution. So the column for storing the sequence was an int 11, which gave us 11-digit resolution. So we sought to increase this by using a decimal field, which supports exact floating point position, and we can go up to 38 digits. Technically, we didn't use any of the decimal portion because to make the migration easier, so we could preserve the existing values while we switch out the column types. So that was the reason. But we still have 38-digit resolution. So this is what the previous timestamp looked like based in seconds. And we took a 13-digit millisecond timestamp and multiplied it by 25 to utilize the full range of the 38 digits. So this makes it better, but eventually you could keep reordering on the same midpoint until we reach the same problem as before. Although that case is unlikely to happen, but we still need to handle it. So if you keep dragging to the same position 83 times, assuming the reorders are spaced 1 millisecond apart, we will reach the same point we saw before. And so I'm going to hand it off to Alice, who's going to talk about how we handle this situation.
Thanks, Sam. So we wanted to automate a job that would ensure we always have enough space between our pins on a board. The objective is to enqueue an offline job that respaces sequences when gaps between any two pins on a board are too small. We have the following requirements. We want to minimize the number of jobs that are running in parallel on the board at any given time so that they are less likely to interfere with each other. And we also want to minimize the number of writes that we commit to the database per job in order to reduce database load. How much space do we enforce then between any two pins? Let's call this the minimum space constraint. So as you might remember Sam mentioning, in the worst case, we can support 83 bisections between two neighboring pins before we encounter a sequence collision. So let's enqueue the job when we have approximately 20 bisections left. Why 20? Well, we wanted to choose a number that was large enough such that we were fairly confident the job would complete in time, but not too large that the job would be triggered all of the time. That means that we want to ensure there's at least 10 to the 6 units of space between any two pins as indicated by their sequence values. So here's a couple of explorations that we took in order to develop the sequence respacing job. The first one was a global respacing approach. That means rewriting every sequence on the board to satisfy the minimum space constraint, starting from the first pin and then adding 10 to the 6 to every subsequent sequence value. Now, as you might imagine, this will quickly run into the same issue as before that we had with pin reordering. It's simply far too write heavy. Some boards have millions of pins. So how can we issue as few writes as possible? We landed on an approach that I'll call localized respacing. And localized respacing involves constraining the sequence respacing to a localized range of pins. Here's a simplified example of how this works in action. Let's say that the minimum space constraint is 2, and you can see that the pin with the sequence value 8 is in violation of this constraint because it only has 1 unit of space between its left and right neighbor. So the first step is we want to grab the left and the right neighbor of the violating pin and respace them. So we'll take 7, decrement it to 6, take 9 and bump it up to 10. And next, we want to repeat this, cascading outward to the left and the right of the current range until the minimum space constraint is satisfied for that entire range. So we'll update 5 into 4 and bump 11 up to 12. You can see now that all of the pins that you see have at least 2 units of space between them. Lastly, we want to identify the edit range and write these new sequence values to the database. As a bonus, we can batch all of these writes to the database in one request. So this approach has several benefits. First, it minimizes the number of writes we need to make to the database by only touching as many pins as necessary. It also reduces database load by batching writes into one request. Now, let's take a look at the underlying SQL. So these two queries are exactly the same except for these 2 highlighted lines. And what they're saying is grab the pin and sequence batches to the left and the right of the violating pin. Finally, here's the query that allows us to update the sequence value for any given pin ID. And now I'll hand this back to Sam in order to cover the results of this project.
So we launched this feature back in March of this year, and on the first day we had around 300,000 reorders per day, pin reorders per day, and 6 months later we're sitting at around 1.1 million reorders. So there's been a 200% increase in engagement since then. And this is what some people on Twitter had to say about our feature. So Surya Biani says, so now you can rearrange pins on Pinterest. I need to express my joy somehow. I'll be organizing my boards like crazy to celebrate. Goodbye, social life, until I see you again. So it's great you really got into it, but sorry for ruining your social life. And then Elena said, I know the Oscars are exciting, but y'all, Pinterest has just made it possible to rearrange pins on a board, and I might cry. I'm so happy. And there are many other similar tweets. So, well, as a bonus, our team also worked on a number of other organizational features. One of these included having the ability to organize your boards into sections. So here's a bedroom decor board, and we can create these sections to organize our pins under different categories. In this case, like color schemes, desks, vanity. And we also use the same approaches we described earlier to support reordering sections. We also built reordering in other surfaces like boards. We built, and so our combined effort resulted in an 80% decrease in community ticket volume These are tickets usually pinners complaining about certain features. So we're really happy to make that impact. I'm going to hand it back to Alice.
Cool. So before we wrap up, lastly, I just want to quickly cover the culture of product engineering here at Pinterest because it is quite unique. So pin reordering was a collaborative effort, and we worked with engineers on other teams like data services. As an engineer on a product engineering team here, you can expect to constantly be working one-on-one with PMs, designs, marketers, and the like. And the really unique thing is engineers have a strong voice in shaping the vision of the product and trade-offs. And most importantly, we help pinners discover and do what they love. Thank you. And finally, we wanted to open it up to the floor for any questions. So if you have anything you want to ask, please make a line behind the microphone stand.
So in the experiments, what was the increase in the load on your database and on the volume? So what was sort of the volume of reordering per board?
So we're for our endpoint, we currently have around 20 QPS and the latency's around 35 milliseconds. So it's pretty fast. It's actually not as much load as a lot of other points. So it's definitely something that core services can handle and our data service team could handle. And when we launched, we just we turned our feature from 0 to 100%, and we didn't have any issues. So,
Great. Something else that I would add to that is this is a power pinner feature. That means that it's a feature for those who are already very savvy with our app and are very familiar. So this is something that we really built to satisfy a small group of users who were really asking for this feature over and over. But the actual most intensive part of this operation that required a lot of resourcing was backfilling the database in order to match the updated schemas that we defined.
Hi, this is maybe a small question, but if you use the minimum space constraint to reorder, wouldn't that mean just one additional bisection would require you to do it again?
So we use the minimum space constraint not to actually reorder the pins, but to ensure that there is enough space between them at any given time. So it's a preemptive step. If somebody is bisecting too quickly, we want to enqueue that job in order to respace the pins on the board out more evenly. But it's not something that gets triggered every single time somebody reorders. Does that answer your question?
The configuration we set guarantees that there's 20 more bisections left. Yeah. And it happens about 1% one out of every 100 reorders.
All right. If nobody else has any questions, then thank you all for coming.
Thank you.